Did you know you can even analyze complex frames without any calculations? In this lecture, I will solve these 4 examples to demonstrate that analyzing complex frames is easier than you think. This is part of my video series on iStructE certificate in structural behavior. Hey friends, if you're new here, I am Dr. Jawed Qureshi, a senior lecturer in structural engineering and design at University of East London, and here I talk about civil and structural engineering. The first example is related to a frame which has overhang portion at the end and joints here are pinned. How do we draw its bending moment diagram? Let us find out. First, I will talk about golden rules and sign conventions. Skip to next section if you have seen it already. Before I go through options, I want to establish some ground rules for analyzing these frames. And the first and the most simple one is that rigid joint maintains 90° before and after deflecting. And here, see that the joint angle is maintained. If you have a fixed joint here, then angle is always going to be 90, no matter if it is deflected or not. This is our first rule. The second one is that fixed support has 0 rotation. This is a fixed support, and observe that there is no rotation or slope taking place over here. The third rule is bending moment is 0 at internal pin. This is internal pin and moment has to be 0 at that point. A pin cannot take moment because it allows rotation. When rotation is allowed, then the resisting moment cannot develop at that point. Once we have established these golden rules, then I will go through sign convention. This is really very important. Counterclockwise shear force, not counterclockwise, clockwise shear forces are positive. Here, observe that the shear forces are creating clockwise forces. In my normal lectures, I would normally have counterclockwise shear forces positive, so that's why I made a mistake here. Secondly, forces pulling an element are positive, so tension is positive in other words. Thirdly, clockwise moments from left sides are positive. Anti-clockwise moment from right side is positive. This is our sign convention. And for shear force diagram, negative forces are drawn inside the frame and positive forces are drawn outside the frame. Reverse is true for bending moment diagram. Positive bending moments are drawn inside the frame and negative bending moments are drawn outside the frame. Let's now go away and have a look at our options. And for this frame, we have to ignore self-weight and bending moment should be drawn on tension side. Now think about it. When we apply loading at the end, what will happen? How would it deflect? Will it deflect towards left or will it deflect towards right? And take a moment to think about it. And there are 4 options to choose from. And grab your pen and draw the deflected shape and find out the bending moment diagram and tell me which option is correct. Put your comment down below in comment section. Once you have done it, then you can skip it to the solution. But for me, if I want to find out bending moment diagram for this frame, I will have to first of all draw its deflected shape, because without deflected shape, I won't be able to draw bending moment diagram because there are no calculations here. In any case, this can't be solved using equilibrium equations because we have 4 reactions here due to pin supports and this is indeterminate structure. The only way we can find out the bending moment diagram and its shape is using qualitative analysis, where you don't need any calculations. You simply use structural intuition to find out the deflected shape, bending moment diagram, and shear force diagram. Let us see how this frame is deflecting. Remember that it will always deflect to weaker side. Here, weaker side is the right side. The reason is that because we have overhang portion and we have pin support over here, so when I apply loading at the end, it is going to deflect towards right. And I'm going to show you a small movie as well to make you understand how it's deflecting. Now, once we have deflected shape, then we will mark the tension side. So here we have tension in column, and here we have tension here, and at this position we have 90 degree. Remember that rigid joints will maintain 90 degree, and here we have tension inside. It is undergoing double curvature. The beam is undergoing double curvature. Once we have deflected shape, with the help of this deflected shape, it would be very easy for us to plot bending moment diagram. It is again deflecting. This is how we draw the bending moment diagram. Because we have tension inside, so that's why we have the diagram inside, and tension at top, so that's why we have tension over here. This point over here is point of contraflexure, POC. Point of contraflexure means a point where a beam is changing its curvature from tension on one side to tension to the other side. Here we have tension over here in the beam and at the bottom. And for moment compatibility, at this point we have tension inside. This is how we draw the bending moment diagram. Remember that point of contraflexure does not take any moment. It's like a pin, so it's like an internal pin. Once we have this bending moment diagram, it is going to tell us really very important information in terms of direction of reactions, and that will help us in drawing the shear force diagram. First of all, let me assess the column. To obtain this bending in column, I should have rightward horizontal reaction here that will cause this column to bend towards left. In the same way, for column on left, to get this bending, the reaction over here has to be leftwards. The leftward reaction will create this bending. And for beam, we have moment over here. To obtain this moment on sagging side, we should have a downward vertical reaction. And for the other part, because we have a point load at the end, to obtain this bending behavior, we should have upward reaction over here. Let us mark these reactions. And once we have these reactions, so on the right side, we should have a rightward reaction. On the left side, we should have leftward horizontal reaction. And in beam, we should have vertically downward reaction. On the other side of beam, we should have upward reaction. Now you would argue that why do we need these reactions? And I will tell you in a minute that we desperately need these reactions. The reason is that we want to plot the shear force diagram. And let us see how we can plot shear force diagram. This is how it looks like. The horizontal reaction over here at left side, it is creating a clockwise moment, not moment, clockwise shear. So clockwise shear should be drawn as positive. And you remember that in case of shear force diagram, negative shear forces or anti-clockwise shear forces are drawn inside, and positive or clockwise shear forces are drawn outside. And reverse is true for bending moment diagram. Positive bending moments are drawn inside and negative are drawn outside. So firstly, it is creating clockwise shear. So clockwise shear is going to be drawn on positive side, and that is the reason we have this clockwise shear which is drawn outside the frame. These two reactions vertical reactions, they are creating anti-clockwise. So anti-clockwise is drawn inside the frame, and you can see it here. It is drawn inside the frame. At the right side, this horizontal reaction is creating anti-clockwise shear, and anti-clockwise is drawn inside. So that's why you will see inside shear force. And these two forces, vertical forces, one over here applied and another over here, and if you observe that it is creating a clockwise shear, these two forces, and clockwise shear is drawn on the positive side. So that's why we have positive shear force at the top and quite significant shear force over here due to applied point load. So our correct option is option C, and this is how we draw the bending moment diagram. There will be double curvature in the beam, and where we have point load applied, we will have huge hogging moment, and the column is going to sag like this. Another column will sag like this. So correct option is option C. Now think about it. If we had inclined column, what will happen? And this is our next question. How about if we have inclined column? Where would this frame deflect? Will it be rightwards or will it be leftwards? Now the dynamics completely changes over here because we have inclined member and we have a point load applied. That will force the frame towards left. If this was vertical, then it will go towards right. But now, because we have inclined member, that will really push the frame to go. And we have to ignore self-weight here, and bending moment should be drawn on tension side. There are four options to choose from, and I suggest you solve this question first before watching this video. Now, which option is correct? It's a hard choice, isn't it? We won't be able to know the correct options till we draw the deflected shape or deflected form. After drawing deflected shape, we will be in a good position to find out bending moment diagram. So grab your pen and draw deflected shape and find me the correct diagram. Is it A or is it B? Is it C? Is it D? Put your comment down in comment section. And don't worry if you get it wrong. I got it wrong for the first time as well. And then I practiced a lot. Now I'm in a good position to explain it properly. Let's see the solution. This is how the beam is deflecting. See that it is deflecting towards left. And the reason is that because we have this inclined member, it is really pushing the frame to deflect leftwards. Now observe one thing here, that we have tension here. There is no double curvature in the beam, and in column tension inside and left column is tension outside. Because we have inclined member, that is the reason that there is no tension in the beam. This is deflected shape. Let's have a look at the bending moment diagram. As you can see, we have tension inside, so that's why we have tension inside. We have tension outside, and the bending moment is not changing at all at this position. At this point, it is being divided into three parts. It's being distributed into three components, and the highest part is the overhang part, where you can see we have lots of bending. At this position, it is bending outwards. Now this is telling us a really very important information in terms of horizontal loads and in terms of vertical loads. Here we will have vertically upward load because the beam is moving up, and here we will have vertical reaction upwards, and at this position, a left column, I will have a rightward reaction, and this rightward reaction will cause the column to move outwards. And again, here I should have rightward reaction as well, and rightward reaction will move the column towards left. That will be reflected in shear force diagram as well. Anti-clockwise shear force is drawn inside, which is negative, and clockwise is drawn outside, which is positive, and the arrow which is pointing towards right, that is creating anti-clockwise shear, and we will go this way and above and this way. This is inside and this is shear force. Note that in comparison to moment over here, there's the amount of moment in the beam is really very small, and that is telling me that the reaction at left side is really very small, and it is zero, the vertical reaction. So that's why we don't have any shear force over here. However, we have a clockwise shear at top. So clockwise is to be drawn on the positive side. So that's why we have this huge shear box at the top. And the key thing to note here is that the vertical reaction at left support is zero. And that is the reason we don't have any shear force on top of the beam. So correct option is option B. And now you can see the beam deflecting. I should have arranged the animation earlier, but because of the sequence of animation, now it's showing the deflected shape. But in any way, you understand now how to draw the deflected shape. So correct option is option B. Now, how about if we have one internal pin and load is applied at the end? Then what will happen? And this is our next question. In this question, we have internal pin on right side. Now, left side, we have vertical point load applied. And similar to last question, we have two pin supports. We have to draw bending moment diagram for loading case shown, and ignore self-weight, and bending moment should be drawn on tension side. There are four options to choose from, and I will not be able to know the bending moment until I draw the deflected shape. Now grab your pen and sketch deflected shape, and then from there determine the bending moment diagram. Which option is correct? Is it A? Is it B? Is it C? Is it D? Put it down in comments. And after you have solved it, now let's go through the options. Especially C is immediately discarded because we have moment at internal pin, which is not possible. Option D and B, they are possible, and option A is possible as well. But if we don't have any bending over here, it means that we don't have any horizontal reaction here. When there's no horizontal reaction on right side, there shouldn't be any horizontal reaction on left side to balance it. So when we don't have any horizontal reaction here, it means that we shouldn't have bending in the column. That's the reason C is wrong, D is wrong, B is wrong. Correct option is option A, but we will draw the deflected shape to find out if this is the correct option. This is how beam is deflecting. And note that we have tension over here, and the column remains straight, so there is no tension here as well. And as a result, we will have a bending moment diagram, which is in hogging. We have vertical load applied, so reaction at this point at left column will be upwards, and reaction at right column should be downwards. And if you follow these two reactions, this is anti-clockwise. So anti-clockwise is drawn on the negative side, which is the inside side. So that's why we have negative shear force here. These two reactions are creating clockwise shear. So clockwise is drawn on the positive side. So that's why this is drawn on positive side. So this is how we draw the shear force diagram in addition to bending diagram. So correct option is option A, where there is no bending in columns because we had one internal pin over there. Let me move to next question. If one element is relatively stiffer than other elements, then what happens? And this is a case where we have left column which has 3 times more EI. EI is flexural rigidity, E is Young's modulus, and I is second moment of area. EI, remember, EI determines the bending stiffness of any member, and a point load is applied. And this structure is indeterminate structure. Indeterminate structure means that this cannot be solved using ordinary equilibrium equations. The reason is that this has 3 reactions at supports, so 6 reactions altogether. Equilibrium equations are 3, so we cannot solve it using equilibrium equations. Structures are democratic. That means that the forces are attracted to stiffer elements if and only if a structure is indeterminate structure. In this case, this is indeterminate structure, so that's why more bending will be attracted to left column than other columns. If this was a simply supported beam, if this was like this, if it was a simply supported frame, EI is same for every bit, then all elements will have equal bending, and then left column in that case will not attract more bending. But here, because left column is stiffer as compared to other columns, that will attract more forces, and this is indeterminate structure. So remember, there's one caveat: the structures are democratic if they are indeterminate structures, and majority of buildings, bridges, whatever you find in reality, most of them will be indeterminate structures. It means that there will be extra elements than needed to provide a level of redundancy in the structure, so that if one member fails, others take over and modify the load path. So the left hand column in the portal frame below is 3 times stiffer flexurally than other members. Which is the most likely bending moment diagram? So we have to find out the bending moment diagram. For this type of frame, we will always have double curvature in all members. Option B is incorrect because the forces are equal over here, and it can't be possible. All members should go through double curvature, which is fine, but all members are taking equal load, which is not fine because this is indeterminate structure, and in indeterminate structure, stiffer elements will take more load. Here, stiffer element is taking less load. Left column was stiffer, it had 3 EI. It is taking less load. So this option is incorrect as well. And option C is incorrect because the beam is not developing any moment, column is not developing any moment, and I don't see the reason why they are not having moment. The joints are fixed. When we have fixed joints, they should have some mechanism to transfer bending. So option C is incorrect. Option D is the only option which is correct one. And here, see that the column and beam, they are having double curvature, and the effect of a stiffer column is that the point of contraflexure, where we have zero bending moment, it has moved up. Normally for other cases it is in the middle, and because of 3 EI, observe that it is taking a lot of load, and this support is taking a lot of bending as well because it is stiffer. So the bottom line is that structures are democratic. They distribute load to the strongest elements. So forces will be transferred to strongest elements. So strongest elements and stiff elements, they will attract more forces in structures. So option D is the correct option. This is how we draw the deflected shape, and this is how we draw bending moment. Again, if I label it, we have tension here, we have tension here, we have tension and tension at bottom, tension at top, tension here, and then tension here. Sorry, we don't have tension here, we have tension at outside because we have fixed support. This is how we draw the bending moment diagram. We will have direction of horizontal force in leftwards, and remember that negatives are drawn inside, positives are drawn outside. And here this force is creating clockwise here, so that's why it is drawn outside. And we will have a downward reaction over here, and upward reaction, and this is creating anti-clockwise shear force, so that's why we have negative shear force over here. And for right side, again, the direction of reaction is towards left, and this is creating clockwise shear. So clockwise is drawn on the positive side, so that's why we have positive shear force. That's how we draw the shear force diagram. So the correct option is option D. Thanks for watching this lecture today. If you want to watch more structural behavior tutorials, then go to this URL or scan this barcode. There are plenty of videos there on trusses, on frames, on beams. And if you wanted to download the lecture slides, you can go to this URL or scan this barcode to download all the lecture slides. And thanks for watching this lecture. I will see you in my next lecture.